Shall I begin, or do you have some words to say?
No, please go ahead, I think.
Good. So thank you very much for being here. It's a pleasure to have this extended time over the next couple of weeks to discuss with you some of the puzzles and the next big steps that we hope to take. It's also always a pleasure to follow Steve, because for many decades, he has brought me questions and problems that I am not able to solve completely, which means there's always more work to do. So let's dive in. The organizers asked me to begin with some very general remarks, hoping that we would begin to engage the master's and doctoral students who are participants in the workshop in what we're doing. And so I'm going to start with some very simple things, and I will, by the end, arrive at things that I don't understand completely, and then I hope we can discuss and maybe even resolve in the next days. So I begin with a voice from the past. It happens to be my voice. More than 40 years ago, I gave some 10 lectures in Les Houches on models for hadrons. And I introduced the subject to the students by saying, if you know the elementary particles and their interactions, and you call yourself a physicist, you ought to be able to calculate the consequences, or at least you should feel guilty if you can't. So those lectures and my lecture this morning are an effort to share my guilt at not being able to calculate all the consequences. However, among the aspirations that I cited at that time, there were three. One was to compute the properties of the hadrons, explain the absence of unseen species, and predict the existence of new varieties of hadrons. That's very close to the central topic of this workshop. And in fact, that's an area in which we've made extraordinarily good, although still frustratingly incomplete progress. Second, to explain why quarks and the quanta of the color force, namely gluons, are not observed. There too, we are short of a full understanding, in the sense that we've not been able to give a rigorous proof satisfactory to axiomatic people and mathematicians that confinement is the consequence of the color force quantum chromodynamics. On the other hand, we have ample evidence that makes us highly confident that colored objects, quarks and gluons, and maybe anything else, are confined to color singlet states in normal situations. And that makes it, of course, tantalizing to try to look for evidence of these things as free particles, which would undermine what we think we learn. And the third goal that I cited was to derive the interactions among hadrons as a collective effect of the interactions among the constituents. That is a very hard problem. It is being addressed now and for the last 5-7 years by people studying the problem on the lattice. Part of the challenge is that the pion is a light particle, therefore the force between protons, for example, or nucleons, is rather long range. And in order to make a lattice that's large enough to confine the pieces of the problem, you have to stand on your head and have very big computers. So we're not there yet, except in the sense that to the degree that we can derive the existence of the particles like the pion and the rho and the omega and so on from quantum chromodynamics with the intervention of lattice techniques, we can then take those as quanta and apply those to nuclear forces. So there's still plenty to do, and I hope someday we'll do even better. Had we been together in Mainz, we might have taken an excursion on the weekend. It's a 50-minute train ride or so south to another lovely university village, university town of Heidelberg. And if you walk the streets of Heidelberg on the Hauptstrasse, you come across a rather imposing yellow building on which there is the plaque that you showed here. Calling your attention to the house in which, in 1959, Kirchhoff began to apply to the sun and stars the techniques of spectral analysis that he and Bunsen, as we say in English, Bunsen had developed, and thus opened the chemistry of the universe. So you walk the streets of these old university towns, and you're in places where things started, and they're very impressive. Not long later, less than a decade later, Sen and Lockyer independently noticed a new line in solar prominences. It's the famous yellow line here, close to but not coincident with the famous doublet in the sodium spectrum. And that was an indication of a new element that had not been seen previously on Earth. The detection on Earth has two parts. An Italian physicist, Luigi Palmieri, saw this line by looking at spectral lines generated from lava from Mount Vesuvius. He's generally neglected in the history because the really definitive sighting came in 1894 from William Ramsay in Great Britain, who not only found the spectral lines in uranium ore, stuff refined from uranium ore, but even gave a name to the stuff, helium, making connection with the sun. So part of my, the point of my first discussion here is that spectroscopy has played an important role through the years, and we've made many discoveries as a result of the study of spectroscopy. So going further, of course, there was the detailed study of atomic spectra. I show you a bit of the hydrogen spectrum at the top, the famous prominent Balmer line there. It gave us many insights into our ancestors, many insights into the nature of matter. This is the motivation for the famous Bohr atom, Bohr's description of the atom. In a couple of papers in 1913. Detailed study of atomic spectra led Gauss-Schmidt and Uhlenbeck to conjecture that the electron had two states that eventually we recognize as the two spin states of the electron. So that was an inference that came from spectroscopy. And then pursuing the object for which Kirchhoff is commemorated on that plaque in Heidelberg, Cecilia Payne, later Cecilia Payne-Gaposchkin, wrote a stunningly beautiful thesis in 1925 in which she made a detailed study of stellar atmospheres. She had schooled herself in the art of spectroscopy long before other astronomers did. And so she was able to make the case very powerfully that the stuff the stars are made of is the same stuff that we are made of. So here are three very dramatic sets of inferences that we owe to spectroscopy, in this case, to atomic spectroscopy. I should say, when you get the PDF of my slides, if you want to go through it, there are many hidden links. You can click on these to link to the papers if you want to study them in more detail. I don't know what, oh, I made a mistake. The links may be hidden, but not hidden enough. Okay, now we move on to nuclear physics, where again, spectroscopy had a definitive result. This time it's X-ray spectroscopy, and the person who did the magnificent work is Henry Moseley in Rutherford's laboratory. In 1913, he studied X-ray spectra of the elements. There were various patterns in the elements that had been observed. People were ordering elements by the masses, apparent masses of the elemental states. Some seemed out of order. They didn't quite correspond to what you would have thought was their order in the periodic table from their chemistry. So following Rutherford's notion that there was an atomic nucleus with positive charge on it, we today call the charge Z or Z of a nucleus, Moseley set out to measure the X-ray spectra. and found that he could line everything up, arranging them not by atomic mass, but by atomic number. This number, the proton, the number of positive charges on the proton. You can see that the data are extensive and also dramatically in agreement with this hypothesis. He was able to order all the elements. This was particularly a challenge for the rare earths, in which the chemistry is essentially identical for all of them. And so the students of the rare earths were very confused about which went where. He was able to clarify that. And he found 3 gaps in the list at elements 43, 61, and 75. Those were undiscovered. They're later found to be 2 unstable elements, technetium at 43, promethium at 61, and a stable element, rhenium at 79. And he furthermore found that the frequency of the line, or the energy of the emission line, was proportional roughly to the charge squared, just as Rutherford's picture would predict. So really fabulous work. That cemented the idea that there were planetary electrons surrounding a small dense charge, a positive charge of the nucleus. Oh, keep doing this. Okay. Later in the study of nuclei came the first of the internal symmetries, isospin symmetry. The motivation for this came from a number of sources. One was, after the discovery of the neutron, the nearly identical masses of the proton and neutron, which suggests that they may be 2 faces of the same state. The charge independence of nuclear forces. One little calculation that you can do is to examine the binding of tritium and helium-3. So a proton and 2 neutrons, or 2 protons and a neutron. And if you fool around a little bit with the likely contribution from electromagnetism, you'll find that those binding energies are quite closely the same. If you look in more detail at level structures and mirror nuclei, you find a resemblance between different states. And for other combinations, here I've plotted for A equals 14. You have the isobaric analog states, so nitrogen 14 has all these isospin 0 states shown in the dark by dark lines, as well as isospin 1 lines shown as the gray lines, which have corresponding states in carbon 14 and oxygen 14. So there's huge evidence that isospin is a good symmetry of the force between nuclei. The third spectroscopy, which arose in the 1950s and 1960s, is the spectroscopy of strongly interacting particles, the hadrons. I plotted here, I've included here a plot from an old but quite charming and interesting article by Vicky Weisskopf in the Scientific American called the 3 spectroscopies. Weisskopf, of course, was a person who had lived through the founding of quantum mechanics and the early applications of quantum mechanics. So he knew what he was talking about for all 3 of the spectroscopies. And he was, as a matter of fact, one of the earliest people to take seriously the idea of the quark model. So even though it's 1968 and no self-respecting person, at least among theorists on the East Coast of the United States, believed in quarks, Weisskopf gives you a picture of that. And it's amusing to see both how one could look forward and how little we all knew 60 years ago, or something like that, 55 years ago. Now, the proliferation of the hadronic states and the patterns that they seem to show motivated Yuval Ne'eman and Murray Gell-Mann to put forward SU3 of flavor, generalization of SU2 of isospin, as a classification symmetry originally for the hadrons. Here I show you the weight diagrams for the meson octet plus singlet, the meson nonette, for the baryon octet and for the baryon decimet. But it was found that this was not simply a classification of symmetry, but that you could use the properties of SU3, Clebsch-Gordan coefficients shown here on the right, in order to relate different transitions and different reactions. And so it became both a classification of symmetry and a useful tool for studying the dynamics of these strongly interacting particles. There was a puzzle. The puzzle was that in contrast to symmetry like SU2 of spin, where in the appropriate kind of system, you populate not just the lowest lying representations, but you could go up and up and up. The only things that had been seen, at least at that time, were the low-lying representations, singlet and octet for mesons, singlet, octet, and decimet for baryons. So independently, George Zweig and Marie Gell-Mann invented what we now take to be the idea of quarks, the idea that you could have elementary spin-a-half particles, flavor triplets, an isospin doublet, that's isospin, and an additional strange particle, the isospin singlet, the strange quark, according to the rules that a meson is made of quark, antiquark, and baryon of 3 quarks. It's amusing that when you look back at their papers, you find that both of them were already open to the idea that there would be more complicated configurations, perhaps at higher masses, but that the dominant ones, for unspecified reasons, should be the simplest combinations of QQ bar and 3 quarks. Even among the people, so there was an early book by Jaap Kokedy from Holland, who put forward the case for the quark model, but even he couldn't bring himself to quite believe it. His preface says, oh, of course, the whole quark idea is ill-founded, quarks have escaped detection, and on and on. And it was very hard to take this idea seriously because the quarks had never been seen. We now turn that essentially to a virtue. Now, the quark model as formulated conflicted with the exclusion principle. Consider, for example, the delta plus resonance made of 3 up quarks, so 3 identical quarks, symmetric in space. It's an S wave, it's a low part of the ground state multiplet. Spin is 3 halves, the spins are all aligned, the isospins are all aligned. So this conflicts with the Pauli principle, the exclusion principle. And you had to either give up the exclusion principle for confined particles or find a dodge. And what came to be the appropriate dodge that seems too easy, but turns out to be brilliant, is to add a label called color to distinguish the identical quarks. This was validated in weak interaction branching fractions. Now you can see it comparing hadronic and leptonic decays of the W boson, for example, cross-section for E plus E minus to hadrons and so on. The next step was to generalize that from simply a label that you could use to shuffle things around to a continuous symmetry, SU3 of color, in analogy to SU3 of flavor, and then to promote SU3 of color to a gauge symmetry. That leads us to quantum chromodynamics, which has this marvelous property of asymptotic freedom that justifies the parton model and offers a path to a confinement mechanism. It's also a if you make a simple-minded analysis of one gluon exchange, it turns out that color singlets are the maximally attractive channels. So even before you do really serious calculations, you can see that this notion gives you a way of understanding why the lowest lying states, and perhaps the only states that exist on their own, will be the color singlet states. So that has led us to our picture of matter. We have quarks and leptons. The interesting detail that the quarks, that the weak interactions, charge current weak interactions, tell us that they behave differently, left-handed and right-handed particles. You see the patterns for quarks and leptons are the same, except for quarks carrying color. So we are often motivated to try to slip them together and make a more unified theory. And we now describe all of the basic interactions by the gauge symmetries SU2, SU3, SU2, and U1. QCD has become the basis of hadronic physics. The fundamental fields are quarks and gluons. We see those in proton structure, hard scattering, matter at high density. They're the essence of lattice calculations. And then we find effective degrees of freedom, which are found in the old notion of constituent quarks, Goldstone bosons resulting from the breakdown of chiral symmetry, spontaneous breakdown of chiral symmetry. All of this plays into effective field theories that have such a strong role in what we're doing today. Tending toward low energy physics, we have isobar resonance models and the nuclei and nuclear structure. Generalization of, or a combination of SU3 of flavor and SU2 of spin leads us to the idea of flavor spin. This is a generalization of a technique introduced by Wigner called SU4 for combining isospin for spin, which was useful in the discussion, the classification of nuclear states. And you can do all sorts of interesting things with this SU6 representations. Among them, to construct wave functions for polarized nucleons, which I've displayed here, and all of the remaining light baryon wave functions. So it's a nice exercise for a rainy day to do these. And then if you make any of a variety of simple-minded hypotheses, you find that this description leads to a not bad description, even anticipation of the baryon magnetic moments. There are things as silly as saying, I will endow each of the so-called constituent quarks, quarks that have an effective mass, which is, say, a third of a proton mass for the up and down quarks. I will, by decree, give it a Dirac moment appropriate to that mass and its charge. And then you work that out and you find that that gives a not bad description of the baryon magnetic moments. So one of the challenges early on was why these extravagantly naive ideas led to successful predictions. And that is tied up with what happens when even massless quarks are confined. You can reproduce these results. And now there are, of course, lattice calculations, which give us a better insight into why these things work. So very tantalizing. And it has often been the case that really simple-minded ideas gave good agreement with experiment, forcing us to ask, how could that possibly be so? Another generalization of Wigner's SU4 is to combine not flavor and spin, but color and spin. This is an invention of Bob Jaffe. It turns out to be a neat way of calculating the residual interaction among different combinations of quarks. And one of the applications that Bob found was that while there is no residual color interaction between color singlets, proton and a neutron, two lambdas and so on, their forces come from, the forces between them come from elsewhere, that there was one state that stood out. You can make the 490 dimensional representation of SU6, color spin SU6. There's a color singlet UDS state, which has a color hyperfine interaction that tempts you to think that it might be bound, might be a stable configuration. That's the famous H-dibaryon, and now after more than 40 years, it has not been discovered in experiment. It has not been ruled either in or out by theoretical calculations. So it's very close, it's on the edge, and the fate is still unknown. So this is a nice technique for the students. If you haven't looked at this, it's a cute way of dealing with the number of calculations that you might want to make, a nice invention. Okay, since the founders had their three quarks, we now have a fourth quark implicated by the Charmonium spectrum. Part of the subject of this workshop, part of the focus of this workshop will be these weird states that are Charmonium associated, but apparently not pure Charmonium states. We have the Bottommonium spectrum with also a number of incompletely unidentified states, shall we say. We've made a lot of progress in understanding these. It's given us a lot of information about the flavor independence of the force between quarks and so on. We even have a few states of the B sub C system, which is sort of intermediate, but more relativistic than the CC bar or BB bar states. So plenty of work to be done there. Now, one of the things that all of us, theorists and experimenters, have to consider is where do we invest our energy? What do we do next? Recently, a little bit before Steve Weinberg's death, we were in correspondence about conservation laws and symmetries topics, a topic of interest to both of us. And that motivated me to look back to some of his ancient papers. And I found in this one some advice to scientists young and old. So he's doing this calculation of quantum corrections to gravitational scattering, which is nuts, right? There's no possible application of this. So he makes an apology. Why am I doing this now? One, because I can. So that's a powerful motivation to say because I can or because I think I can. And the second, I think, is quite important. It is because something might go wrong and that would be interesting. Now, in this case, nothing does go wrong. You can find applications of this all around us. I think in particular, the discovery of the accelerated expansion of the universe. There are some people who thought they could use supernovae to measure the deceleration parameter. So, okay, they thought they could. That's because I can or because I think I can. I don't know whether they thought something might go wrong, but to outside observers, everybody knows the answer is going to be the deceleration parameter is 2. You don't bet against Einstein, so why would you do that? But something might go wrong, and in that case, what went wrong turns out to be the biggest by volume and energy discovery in the history of the universe, the accelerated expansion of the universe. So I think this is something we might think about when my colleague S.D. Eichten and I urge experimenters to put more attention on the B sub C system. It's precisely because something might go wrong. This is something that we ought to be able to calculate, but maybe there are bigger relativistic effects, or maybe the unequal masses of the quarks bring in something that we didn't anticipate. So I think that's a good motivation to look for something that might go wrong. So let me just say a few words quickly about things that we will be looking toward in the next days. It's very nice to have models, and one of the things that we do with these new states is to make simple models for them. Say, I've got a picture, this is the way it's going to go. We have to advance from those models to controlled approximations, of which luckily we have developed a good number, and we'll be developing more. There's non-relativistic QCD and its variants for heavy systems and others, an expansion parameter V over C, heavy quark effective theory, which we use in a number of settings, where lambda QCD over the quark mass comes into play. Chiral symmetry for the light quarks in the first instance, giving an understanding of the lightness of the pion. Lattice QCD, of course, being the cosmic tool, as long as we can make it work. So the growth of effective field theories, the growth of non-perturbative calculations are not only a supplement, but an extension to the simple model pictures that we make. And that's where a lot of our progress is coming. It's very important in the framework of effective field theories to try to figure out what are the relevant degrees of freedom. One that has taken on more popularity of late is the notion that diquarks may be useful constituents, useful to think about as constituents. We've known for a long time there are correlations among the quarks that are not taken into account by the SU6 wave functions. We also know that 2 quarks are attractive in a 3-star. And so in the extreme limit of super heavy quarks, it surely is reasonable to think of a compact diquark with color charge 3-star, color representation 3-star is right. Question is, as you go away from that extreme limit, how does the mixture of 3-star and 6 change? What is the interplay of that with the hadronic states into which things would eventually dissociate and so on? That's one of the problems I've been thinking about, with no great results to report to you this week, but maybe sometime soon. And of course, there are notions of diquarks and tetraquarks in the explanation or interpretation of the scalar nonnet. So I think one of the things that's very important for us too is to try to extend this idea. There are places where, as we've just seen, where it seems highly plausible to think of compact diquarks. In other places, the diquarks clearly have a finite extent. How much can we take that into account? How do we make that a systematic and quantitative study? And there are all sorts of ways of doing that, some of which I've named here. So I'm going to close with two injunctions to us as theorists in particular. It is very attractive to latch on to a simple picture, to say particles like the X3872 might be mostly a Charmonium state, or mostly a molecular state, or a pure tetraquark state, or something else. We live in a quantum mechanical world. Surely all of these things are going on. And so how do we fit them together? So rather than call attention to the incomplete work of other people, I'll call attention to incomplete work that I've been involved in. When we studied the possibility of Charmonium states above threshold, we estimated the open charm content of the CC bar levels. So that's a couple channel study that at least acknowledges that other things are happening, but we did not consider the interplay with molecular states or tetraquark states, or examine exhaustively the influence of threshold cusps and stuff. Now that's a lot of work to do all that stuff, but we're now at a point where the accumulating data, not just of X, but of the other states, really motivate us to try to not just get the big picture, but strive for a full understanding. So maybe we can do that. That's not going to be the work of a day or a week, but I think it's very important. I'd like to advocate for the study of doubly heavy baryons. They're useful for engineering purposes, namely for estimating the masses of stable doubly heavy tetraquarks. They also have relationship to heavy light mesons. We may in time be able to learn about excitations of the core, and there may be things we learn about funny states like BCQ that expose the limitations of non-relativistic quantum mechanics. The weak decays are going to be very rich and therefore fun, and maybe we isolate different pieces of the weak interaction Hamiltonian. Now I noticed that my friend Stan Brodsky awoke even before sunrise in California and is here. So I give an assignment either to Stan or to the rest of us associated with Stan. Stan has recently advocated with his collaborators a QCD supersymmetry that relates mesons to baryons and to other things. So one question I would pose is, are there any lessons either from this or to this from the studies of supersymmetry in nuclei? I have to say those scare me because when we talk about the level structure of platinum and things like that, just too complicated for my little mind, but others may do better. Second, and this is more immediately relevant to what we're undertaking in these 2 weeks. Stan will show you relations among masses of mesons, baryons, tetraquarks, pentaquarks, who knows what. There are similar relations that come from heavy quark symmetry. So how do these relate to each other? Do they have a common origin in some cases? Can we combine them to get more results and so on? So I think paying attention to all these things is going to be fun. And I hope it's something that will lead us to new understanding. Lastly, QCD could be complete to very high energies. How might it crack? How might it upset what we're doing as spectroscopists? Well, there is a strong CP problem that needs to be solved. Probably doesn't overturn spectroscopy, but who knows? The factorization certainly doesn't hold in every situation. You can imagine kinematical cases in which that breaks down, but without anything fatal happening. Maybe there will be free quarks in unconfined color. Maybe we'll discover new kinds of colored matter. Maybe quarks will show themselves as composite, or maybe we'll discover that QCD, that SU3 of color, is part of a larger symmetry group that tells us more. So with that, I'm going to stop. I would just remind us that models are great exploratory tools. Engaging the lattice and symmetries at every opportunity is helpful. We need to tie together the different approaches of different people. Of course, have to tie together theory and experiment. Going between systems. So for example, Charmonium, Bottommonium, B sub C is a way of stressing our models, relating mesons and baryons and so on, and looking beyond the SOTUS things. And not just doing what we were doing yesterday, but try to choose our problems so that we focus on things of lasting value. At that point, I'll stop and I'd be happy to take questions or comments.
Thanks a lot, Chris, for this very nice overview. So I think you have given us a chart of what we should look for. And I mean, you mentioned BC spectroscopy, and so that's I think hopefully we will have some time to discuss. Any questions?
More than question, I just have a comment. The talk given by Steve and now the talk from Chris is very nice. I mean, it goes from old important topics to modern physics, and this actually offers the hint for discussion. I was just having a look now to slide number 24, the slide before the conclusion. You address actually a lot of problems that probably in the discussion this afternoon we should go through and develop somehow. That's all.
Thank you.
Yes, please go ahead, Emilio.
Yeah, yes, I mean, there are not many people, I mean, volunteering to ask questions or making comments, so let me say something. I mean, when you establish the analogy there with the supersymmetry, nuclear or Yakello and all that, this is nice, of course, but you know, I mean, there are differences between quarks and anti-quarks. For example, I mean, if you go, I mean, there and you look, for example, at mesons, for example, take DD bar or DD. So you see, I mean, with theories, I mean, that will come, I mean, during this workshop. I mean, the DD bar, I mean, gets bound. The lattice people, I mean, well, there were theoretical predictions for that, but the lattice people lately, I mean, are also supporting this, that there is a bound state of DD bar. However, there is no DD state. DD state, I mean, doesn't get bound in this wave. And there are things, you know, for example, like, I mean, there's the identity of particles. DD, I mean, is identical. DD bar, they are not identical particles. So, you know, there are subtle differences, you know, I mean, it's not as simple as that. So anyway, I mean, that is a comment I wanted to make. I mean, because analogies are fine, but when you go there to the fine tuning, I mean, there are subtle differences that one has to take into account.
How can one disagree with that statement? However, I would say that one of the possibilities of the study that a number of groups have now made from antiquity to the present time of stable or quasi-stable tetraquarks containing two heavy quarks leads to states that have quantum numbers of DD. Such a state has just been seen by LHCb, in fact. So that's, I think that doesn't contradict your point. It illustrates your point that we need to be subtle.
Okay, good.
We didn't hear you, Emilio, if you were, okay. Okay, so I think we are very good on time. Any other question? So maybe not.
Am I allowed to make some other comment?
Yes, please go ahead.
Yes, I mean, yeah, I mean, sorry, I mean, because since no one wants to talk, then I think we should, you know, when you talk, for example, about, I mean, the low-lying scalar mesons, I mean, and you talk about the possibilities of having like diquark bar, or I mean, meson. I mean, when you sell QQ bar or QQ bar, I mean, on the pentaquark nature, I mean, we would agree. But certainly, I mean, one doesn't have to exclude anything at the beginning, and one should look at everything, and God knows, things might be just a complicated mixture of everything. But I think, I mean, what one has to do, I mean, and you pointed that out, I mean, as comment, that what one has, I mean, some model, one has to go ahead, you know, and make predictions. Lots of predictions, as many as you can. And so far, I mean, the highest number of predictions, I mean, have been done for these knowledge of the scalar mesons by the picture of QQR interacting with QQR, let's say meson picture. I think, well, I mean, that's of course my favorite, but I also, I mean, accept, I mean, that things could be more complicated. Yet, the amount of checks that have been done from this picture is overwhelming. I mean, much more than from the other picture. Yeah, that's all.
Yeah, that, as you know, is a subject which has been under close scrutiny for many, many years. It's not simple. And I think we can all admire the immense amount of work that's been done.
Okay, good.
Okay, thanks again, Chris. So please don't go away. So we reconvene in 15 minutes at 2:15 for the next session.